Okay, welcome to Time Travel 2. More on time travel. This time we'll focus a little bit more on the physics instead of the paradoxes. So we just had a lively discussion here. So this, I would guess, leads to lively discussion. So it's a lot of fun, which is physics should be fun. So we don't know all the answers. It's just fun to debate this thing. So I'm Robert Namaroff. This is Michigan Tech. We're talking about time travel. And the course is Extraordinary Concepts in Physics. There's actual students here. It's being taught for credit called Physics X. You can find things on Google by searching for these terms there or on iTunes. And so let's get to the machines. So what could allow time travel? So let's look a little bit into the physics of this instead of the paradoxes. So faster than light movement or information transfer might allow time travel. Unusual cosmologies might allow them. Black holes, cosmic strings, wormholes, and something I didn't know about before investigating this lecture, what I think is called the Alcubierre drive, which seems to be getting some play in the literature. So I'll review what I've read, although much of this I've been thinking about for part of my career life, because it's really a lot of fun. That one I am reporting on like a reporter. Okay, so faster than light travel. So let's say you have an A and a B, an Alice and a Bob, and Alice flashes her light. When Bob sees that light, he flashes his light. So all observers moving slower than the speed of light will agree that Alice flashed her light first. So if you have Alice here with her light, and Bob here with his light, and this goes off first, you can put observers here, 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 anywhere. And they will see that A flashed her light before B flashed his light. So cause and effect is well established. So now Alice flashes her light again. But before Bob sees that light, how does he know when it's going to occur? He doesn't, so he guesses. Okay, he guesses. So Alice flashes her light. Before Bob sees the light, he flashes his light. Now, no information was transferred because Bob didn't see the light. So no signal was sent. So let's put observers around again. So an observer here near Alice will say, well, Alice flashed her light first, and then Bob flashed his light. But an observer near Bob will say, oh, no, no, no. I saw Bob's light flash first. So Bob flashed his light first, and then Alice flashed her light. Therefore, you cannot establish cause and effect here anymore. Cause and effect is lost when you have faster than light communication. So if you could send a particle and do the same thing, then you would not have cause and effect. Therefore, faster than light particles like that travel you've lost cause and effect for that. Therefore, extending this scenario, it's possible that Alice might see Bob's light before even Alice was going to flash her light. Now, I've thought about this, and I have to admit there's a bit of a disconnect, but everyone says it's true, so we can think about that. So anyway, since this is thought to have happened, this shows that, assuming that faster than light communication allows backwards travel in time, because Alice could then see a flash from Bob before she flashed hers. So she got a communication from Bob saying that she flashed her light before she flashed her light. So that's traveling back in time. So that's the basis for faster than light travel being connected to backwards time travel. Mass, however, you cannot take. So let's talk about faster than light now, FTL it's called. It's its own field. People publish on this all the time. No particle has ever been seen to travel faster than the speed of light. As we saw with the two slit experiments, you cannot send signals faster than the speed of light. You can't tell somebody something, although in some ways it seems like correlations can exist that seem to travel faster than the speed of light. But anyway, you can't take your favorite bowling ball, you can't hit your tennis ball faster than light. For one thing, if you were to accelerate it, if you were to charge up your tennis ball and accelerate it uniformly, it would not be able to cross the light barrier. Its mass would become arbitrarily high the faster it went relative to you. At some point, it would start banging into things and splintering into lots and lots of particles, which particle accelerators do all the time. So particle accelerators are trying this, except they're using much smaller things than tennis balls. So you can't take your tennis ball and accelerate it faster than the speed of light. It can't cross that barrier. However, tachyons, the classic name for things already traveling faster than the speed of light, may have always been traveling that fast. So maybe people say, you can't cross the barrier, but things can exist that are already on the other side of the barrier. These things, however, violate causality, and they can strike you before you can see them coming. As was done with the scissors paradox in special relativity, however, you can suddenly, when you might see two images of a tachyon that just passed you, one moving away from you in a direction of the tachyon approach, and one moving away from you in the direction the tachyon is moving away. So you can see two images of the same thing. So tachyons are strange things. Again, we don't have first-hand knowledge these things exist. Many people think they don't exist, but they're fun to think about. So let's delve into special and general relativity a little bit and say that Google Docs decided to make this small for reasons I don't know, but we've had this slide before. A time-like interval is when one event can affect another without a backwards time machine. A space-like interval is when one event cannot affect the other, again, without a backwards time machine. So in time-like interval, it's not a problem. So you can go and clunk your friend on the head, and that's fine because it was a time-like interval. A light-like interval is what light does. That's what Alice and Bob were doing. However, a famous thing, it's hard to see, I'll write it here, is a closed time-like curve. And that's a signal in physics, in relativity, that there's backwards time travel around. So that's closed time-like curve. Oops, that's undo time-like. So sometimes called closed time-like loops. So they are actually allowed in general relativity. Again, the microphysics allows things that the macrophysics does not. So if you could find a closed time-like loop, then you would just have to coast on it, and you could go back to the same place you were, but at an earlier time. So that's why all these conjectures, these paradoxes came up last time. Other physicists then come in and say, well, general relativity allows the trajectory, but there are other things that come in that disallow it from other physical reasons. So Einstein was a fan of thinking about these things, made tremendous contributions. Kurt Gödel, a famous mathematician, was at the Institute for Advanced Study at the same time as Einstein, published inconsistency conjecture, which is amazing. He gave Einstein a present in the form of a theory of a cosmological solution, in fact, a general relativity, that admits simple time-like curves. So it showed Einstein more clearly than something he might have suspected already that in this cosmology, you could coast on these closed time-like curves and get back to where you started. This cosmology has lots of those. Okay. So another way that gets a lot of work these days in movies and science fiction and otherwise in actual physics journals is the idea that a black hole can be connected to a white hole through a shortcut in space called a wormhole. So generically simple wormholes would kill anyone, however, who entered them, compressing them to an infinite density. This is your simple black hole. It's the throat between the two, were it to exist, would be infinitely dense. And humans can't go through something that's infinitely dense. It kills us. However, people think that you might be able to hold up that infinitely dense hole and make it not infinitely dense by putting in some kind of dark energy. So this is commonly debated. If you could connect a black hole through a wormhole to a white hole, you could then, for instance, communicate faster than light, because it would go, well, we'll explain that in future slides here. So here's what you do. You have a black hole connected to a white hole. So you consider each one side of the wormhole. Theoretically, you can go in either way, since a white hole has the same gravitational solution externally as a black hole. If you don't understand that, you can go back and look at the other lectures and links. So you take one end of the wormhole now, and you bring it near a black hole, another black hole. So there's a big black hole. So you're at one end of the wormhole here, and your other end of the wormhole here. Now, when this end of the wormhole near the black hole is going to be in a gravitational field, so time is going to run slowly for them, particularly as seen from the other wormhole. So then you let lots of time go by. and time slips, and the relative time between the two get out of sync. So it's like one watch running slow, one watch running fast. You let the two run at way different rates for a while, and then you bring them back, and you move the one outside elsewhere in the universe where you want it to go, maybe up here. So then what happens is you can go in one end of the black hole, of the wormhole, and come out the other end, and time would be different. It wouldn't be like having to travel through the two at a speed constrained by light. For instance, if you were to bring this one actually back right next to the other one, the times would be different. So you could go in one and then come out the other one at a much earlier time, even if they're right next to each other. So you can consider them to be two phone booths, or two police boxes, if you like Doctor Who. You go in one police box and you come out the other one years earlier, which happens on Doctor Who on occasions, but they don't get into many times the wormhole explanations. Okay. So here's a classical image of this, including these distorted grids that make everybody feel they understand these things. The first idea was given by Einstein and Rosen in a paper. It's called an Einstein-Rosen bridge, another word for a wormhole. So here's something thought to be a black hole, and here's the other end, possibly a white hole, and what connects them is the wormhole, also called an Einstein-Rosen bridge. Okay, there are other ways that people have come up with time traveling in general relativity. For instance, there's something called the Tipler cylinder. So it's just actually an infinitely long, very massive cylinder. So one would think these infinitely long cylinders occur in introductory physics all the time. But what you didn't know is if you actually spun it, it would cause frame dragging, and then if you were to have paths that went near it, particularly acceleration near the cylinder, you could come back to your path, and if you integrate things right, you find out that you come back to the same place at an earlier time. So the Tipler cylinder allows closed time-like loops. Isn't that interesting? So people were amazed by this. Something so simple allows time travel. Why don't we just build one and go into the past? Well, it turns out that, again, the more sophisticated analysis shows the cylinder really must be infinitely long, or it doesn't work. So we can't make an infinitely long cylinder, so we can't get this to work. Last one is something, well, I'll guess at the pronunciation, the Alcubierre drive. I think it's a Mexican physicist came up with this, and it was an attempt to create a real warp drive like in Star Trek. So there's a bubble of space-time, which could be something like dark energy in black holes or something like that, that moves with the ship and creates time dilation in this bubble. Therefore, which can make it move faster than light when compared to distant observers. Inside the bubble, motion is slow. Nothing moves faster than light. The physics is controversial, and people are publishing papers on this back and forth. One might need negative energy like localized dark energy, whereas most dark energy is difficult to localize. And if you take dark energy like a domain wall of dark energy and fold it into a ball, it no longer acts like dark energy. So it might require negative mass, which we don't think exists. But somehow, if you could create localized dark energy, you might need a tremendous amount of mass again to get this to work. At worst, one would think that, according to the analysis I've read, one could not communicate with the front of the bubble. So even though this seems to be a time travel device, you can't communicate between the two time travelers. And also at worst, the Hawking radiation might be deadly. At worst, this just doesn't work, and it's currently being debated in the literature today. So with that, and the possibility of the physics of time travel, I will ask you to come visit me in the past and tell me that all of this is wrong and here's the real solution. I will see you in my future and your past. Bye.